Welcome to this episode of Gov School Rocks, where we learn to speak rock and where we learn to listen to what the environment has to tell us in its stories. Today we're going to talk about igneous rocks. Igneous rocks were the first rocks that existed on this planet. When the Earth formed 4.5 billion years ago, it's thought that the Earth's surface was pretty much covered in molten rock. Well, the only rock that can come, if you remember your rock cycle from 9th grade, the only rock that can come from molten rock is igneous. So all the early rocks, the earliest rocks on Earth, had to all be igneous. The oldest rocks we have on the planet right now that we've dated are 3.8 billion years old. There may be one that's 4.1 billion years old that's been found up in northern Canada. The problem is that all the rocks that go back to that time period, or there were no rocks that go back to that time period. So the only way we can date the Earth is by using chunks of meteorites and asteroids, which then give us a date of 4.5 billion years. So we use radiometric dating for this, of course, and that's important to understand. We'll talk about that in another episode. But initially, the first igneous rocks were probably mostly like, or most closely related, or most closely look like these dark-colored rocks, which in the igneous world we call mafic. Sometimes some people refer to them as basaltic, because originally the Earth's molten magmatic surface would have been relatively consistent in terms of its iron and magnesium being very, very common elements, not as much silica. And as that surface began to cool and some of the lithospheric plates begin to crystallize, the rock is still remaining. The rock that forms is what we call ultramafic or mafic at best. Ultramafic means it's very, very rich in iron and magnesium, very much like current mantle rocks are. And of course, remember the mantle is solid, not liquid. So mantle rock is very dark in color. We call it basalt, or it'll be very kind of greenish in color because of the olivine in it. And things like peridotite, for instance, is a great example of that. Or there's also rocks that no longer are formed today, like komatiites. We call them fossil rocks because at one time they would have been common, but now they're not. Or they don't exist at all anymore. As time progressed, and as these solid plates began to be recycled, because plate tectonics had to get started at some point, other forms of lithosphere began to develop, leading eventually to, this is what we call an intermediate lithosphere, or an intermediate rock, or andesitic, named for the Andes Mountains in South America. But andesitic rocks are a mixture chemically between, or midpoint chemically between mafic and felsic rocks. Felsic rocks, like this granite here, which you can take for granite, have a different chemistry. So they have much more silica in them in terms of the minerals that are composed of the rock. But there's something called, there's specific minerals in here that are indicative of felsic rocks, like this pink feldspar we call orthoclase. So this is a mixture of orthoclase, feldspar, quartz, maybe a little bit of plagioclase, probably some pyroxene, maybe even some biotite in here. But this is a really nice granite. So if I were to put these on a continuum, I'd put my granite over here as the felsic rock. In this case, this is kind of an andesite. I might call it a porphyritic andesite because it's got a lot of large phenocrysts of minerals in there. But anyway, it's intermediate. And then we can put our more mafic rocks over here. So igneous rocks occur on a chemical spectrum. And of course, how they're formed initially is important to understand. And the crystal size tells us something about where they're formed, where they cooled, whether deep within the earth where the crystals are larger, or on the surface as part of volcanic activity where they get cooled very, very rapidly, and can produce things like this obsidian, which even if you look closely has a nice layered effect to it, which is kind of cool. So obsidian is volcanic glass. All right. You also have other forms of obsidian that still have lots of holes in them. This is another volcanic rock formed on the surface. So it's got the same kind of chemical makeup as a mafic rock in this case. This is Hawaiian type lava. You can see there's a lot of holes in it, so it's vesicular. That texture tells me something about how much trapped gas was still in here when this cooled. Quite a bit of trapped gas. Most of that trapped gas is actually water vapor, among other things. So these are volcanic specimens. This is another volcanic specimen, which is nice and light. If I put it in some water, it would float. It's a form of pumice. A lot, you can see, it's also got a vesicular texture, which means, of course, it's got a lot of pore space. And that's what makes it so lightweight, is all that pore space in there. So that's another volcanic rock. So igneous rocks, we can describe igneous rocks based on their composition and texture. There's also a whole other way of describing igneous rocks based on their chemistry. And that's a little more complicated, but it's also a lot more specific. And you go someplace like Kenya, for instance, the East African Rift Valley, where you can have a variety of different kinds of igneous materials there. So this came from Kenya. This specimen also came from Kenya. They're very similar in their chemistry, pretty mafic. But you can have also other kinds of chemical chemistries going on in terms of the igneous materials being produced there. You may be familiar with granites and so forth in terms of countertops, right? So this is a chunk of countertop. This is almost a gneissic granite, a little bit of banding going on here. So it's gone through a bit of metamorphism or some heat and pressure without remelting. The important thing about igneous rocks is that any rock can become an igneous rock. Okay, I mean, any rock can become any part of a rock. That's the whole nature of the rock cycle. It's just that the crystals have grown together, not necessarily under any significant amount of pressure, but what you have happening is a liquid becoming a solid, and that's what the nature of igneous rocks is. Now, which igneous rock you get is dependent on the chemistry at the time of that magma chamber, or in the case of volcanic materials, the type of volcano and the tectonic setting of that volcano. This is ash from Mount St. Helens 1980 eruption when I was 1 year old. This ash is just broken up bits of rock and would have been superheated when it came out of the volcano. But it's indicative of what the top of that volcano looked like. And Mount St. Helens is sitting on a subduction zone in the Cascade Mountains. So subduction zone tectonics versus mid-ocean ridge type tectonics versus transform boundary tectonics. Those, among other things, is it an island arc like Japan? These things determine the chemistry that you're going to be dealing with. And it's important to note, because of plate tectonics and the constant recycling of this rock through the Earth's interior, the surface of the Earth, its plates, and the mantle, they've all been altered over the course of those 4 billion years. It's also important to note, igneous rocks are not just igneous rocks, they're also very important for life. These rocks, to me, represent the primordial sources of all the elements that make life possible. The carbon, the hydrogen, the nitrogen, the oxygen, the phosphorus, the sulfur, the chnops, as we sometimes refer to them in astrobiological circles, the chnops elements, all of which have their primordial source in the Earth's interior, where these rocks are getting ready to form. So that's really important. How can we connect our current living environment to the Earth's interior, to igneous rocks? It's important to remember where everything you see around us came from. It came from the Earth's interior. So anyway, that's it for this episode. Next time, we're going to talk about the other kind of crystalline rocks, metamorphic rocks. So see you then.